Good day, welcome to this video. In this video I'm gonna be showing how to code an average current mode control routine for an interleaved boost converter. Obviously the same method could be used for an interleaved buck converter, but the PID control coefficients will have to be changed. Obviously will have to be modified to use with other types of converters. But in this particular example, we'll be using a boost. And so I've made other videos talking about how to um going sort of in depth at the origins of the PID controller equation. So this particular equation right here on the origins of that. So I'm gonna link those because this video is basically just an average current mode control. Only this time it's interleaved, so it's been applied to two buck converters essentially. Because they're sort of out of phase with one another. So this is the Proteus I guess Proteus design schematic. More like schematic. So this is it. So it's two boosts converters basically interleaved with one another. And yeah, so that's just to give an idea, a picture of what it is. And the procedure is just the same as a normal average current mode control. Only this time there's two inductors to be taken care of. So and also this particular video is done with this particular PIC 24. It's not, this is not the best sort of pick to do this with. It could be used obviously with this, but as this video will show, this could be used, but it's important to note you could get much better performance on a digital signal dedicated to the processor. This is a PIC 24. It's kind of made for other reasons than digital signal applications. So anyway, so this is, but if you wanted to use this is how you essentially go about it. So obviously here the three sensors to be used: AN0, AN1, and AN2. So AN0 is the voltage, output voltage sensor, and AN1 is the for the first inductor, AN2 is for the second inductor. And there have to be two, how do you say, there are two MOSFETs being controlled, so two outputs are needed, OC1 and OC2, controlled by two different timers. So essentially the PWM has to be out of phase, and this particular controller does not have that feature where you can make it automatically out of phase, so you have to sort of do it manually, which is done in this case. So OC1, output capture 1 is controlled by timer 2, output capture 2 is controlled by timer 3. So that's, you can see, output capture 1, timer 2, output capture 2, timer 3. I know this area's got sort of boring, so if you're not going to use this microcontroller, just feel free to sort of skip this area here and just skip right to the point where I'm talking about explaining the code, because this might be quite boring if you're not going to use this particular microcontroller for this. And the timer 1, obviously that's where the control routine is, and that happens every 130 microseconds. But this is for the current loop. So there are two loops in an average current mode control algorithm, I guess. So there are two loops. There's an inner loop, fast loop, and an outer loop, which is a slower one, which is for the voltage. The inner one is for the current, so it's 130, and it's made 130 microseconds here because this microcontroller cannot go any faster than that. So that's why it's 130 microseconds. Alright, and so timer 2 and timer 3 is set up because they're controlling the output capture. The switching frequency is selected to be 100 kilohertz, so that's 10 microseconds as usual. And yeah, that's that. And for the ADC, these three are selected: internal counter, end sampling, and starts conversion. And auto sampling is enabled, so we can access the ADC readings. Um, yeah, and UART is basically to see the results. This is more for debugging purposes. It's not necessary for normal operations. Alright, so that's that. And as for that, and as to create a phase shift, so this phase shift function was basically added, and essentially what it does is it stops both timers, and then it starts timer 2, starts it at 0, starts timer 2. Let me just zoom in there. So it starts timer 2, and then it constantly checks that timer 3. If timer 3 has reached half of that of the count of timer 2, um no, sorry. Once timer 2 has reached half of its completed value, like counting, because it's counting from 0 to the maximum. So once it reaches half of that, it starts with timer 3, and then whatever's produced by whatever output captures connected to timer 3 is permanently out of phase with whatever's coming out of output capture 1, which is tied to timer 2. Let me just explain that again. So timer 2 is started first. So once timer 2 starts, when it gets about halfway of where it needs to be, then timer 3 is started. And output capture 1 is attached to timer 2, output capture 2 is attached to timer 3. So in that sense, output capture 2, the PWM coming out of output capture 2 will always be 180 degrees out of phase from output capture 1, which is the first PWM, which is attached to timer 2. So that's essentially what this entire thing does. It checks this valid. So while valid is going to continue this loop, and then once it gets past half, once timer 2 value gets past half this phase val, which you have to um I guess initialize or select rather, and once it gets past that stage, timer 3 is zeroed out and then started, and then it's OC2 is also started, and that's how the process goes. And so this loop will never happen again, and it's called from the main function. And as you can see here, the maximum value for the count is 159, but here it's 60, it's not half, because there's some weird kind of delay, so you kind of have to do a trial and error thing to get it right. I've heard there's another way to sort of tweak this. I'm yet to find out that way, which is apparently much easier than this. So, um, you should probably look around on the internet for a better way, because I think this way might be a bit, out there in terms of you have to make another function. So if there's an easier way, you should go ahead and do that. And keep in mind that digital signal processors, you do not have to do this. Um, there's a there's an inbuilt how do you say it inbuilt option to have out of phase PWM, so that's quite nice. Yeah, so that's that. So that's basically the basics for everything, well, the foundation for this particular system, for this particular example. um yeah, all right, so it's basically the same as an average current mode control um converter. Like I said, now there are two reference currents. So you have first the VREF, and now you have the IREF for the inductor 1, IREF for the inductor 2. And then you have the total IREF. Then you have I actual 1, I actual 2. This is for the actual current reading that's read from those inductors. And you have the V actual, which is the output voltage. And also you have here the array, the PID array. And this time we have one for the inductor, for the error array, and this is the PID step output array. And we have another one for inductor 1, which is these two lines here, and then inductor 2. And that's that. And this is obviously for the outer loop and the inner loop. Alright, so that's that. And now for the in timer 1, this is where the actual loop is at. The main code is at for the PID control. Alright. So at first you have to sort of get the readings for the voltage, the actual, and then for the current for both inductors, I actual 1 and I actual 2. And so basically here, um this value represents the large voltage, sorry, the bigger resistor in this, because it's a resistor divider, and this is the smaller resistor. And once you sort of do a calculation of these two lines up here, you come up with this particular line. This is not included because of controller processing time. This takes, to add those takes more time than to just execute this line. And the same for I actual 1 and I actual 2. So in Hall effect sensor is being used for them. So that's why we have here 0.1, it's 100 millivolts per amps. That's how it works. So the first line here for both the current and the voltage and the current, this is essentially to convert it to real world voltage, right? So whatever is being read is a digital value between 0 and 1023. So you want to convert that to a voltage scale, and that's what this line does. And then after that, you want to take that particular voltage and convert that to the actual current, or in this case, the actual voltage. So here you have to scale it back up in the code according to your resistor divider. So in this case, this is 1.2 mega ohm, 20 kilo ohms, right? But in this case, so because it's 100 millivolts per amps and the offset is 2.5 volts, so you sort of have to say 2.5 volts minus the actual current. The actual voltage reading read by the microcontroller in that particular pin. And it's important to know that this is the VREF for this particular microcontroller. This is actually not 5, it's 3.3, but in Proteus it's 5 for whatever reason. It's just 5. So that's why it's 5 here. Just keep in mind some more advanced microcontrollers like digital signal processors have 12-bit ADCs. So this value here will be 4096 and this will be 3.3 volts, depending on what the microcontroller is, right? So you have to sort of find out what that is. I think for some Texas brands it's 3.3 mostly, or I guess some have 3.3, some have 5, but just check and make sure this particular value here. That's important. Remember, if you're not sensing the proper values, you're not calculating the proper values, you're basically not going to control anything, right? Well, you might control something, but it's just going to be off, and you might destroy your components in the process. So it's important that this is in order, and that you redo the calculations, because this is for a 10-bit ADC and 5 volts VREF, and the current sensor in this case is 100 millivolts per amps. In the case of the 30 amp sensor Hall effect, ACS 712 30 amp specifically, it's 66 millivolts per amp, so this is going to be 0.066. But in this case it's 100 millivolts, so it's going to be 0.1. All right. So that's that, and now you have here IRF1. So now you have to sort of um how do I put it? So here, okay, let me explain the voltage loop first, because that won't make much sense now. So for the output voltage loop, so it happens 20 times. In this case, I made it 20 times because I'm trying to be conservative with it. So what happens basically every time this loop gets completed, this particular variable vloop count gets incremented, and only when it's 20, when it's gone up to 20, that's when this particular loop will be executed, right? So the first thing it does when it goes into the loop is it goes back to 0. I mean, it makes it 0 again. Then it executes, and it executes the loop. So this is the PID. This is PID control. Um, velocity mode PID control specifically. So these are the steps. So this is the first step, PID control step, and then the error for the error as well. So basically this is the previous PID control step being equated to the current PID control step. Obviously when it does this for the first time, this particular value will be 0.0 as initialized, and this is the previous error, the current error of the, and equated to the previous error, and now this is the previous error equated to the current error. Okay, and then now you update the current error value, and then you execute the PID control loop. Please do watch the video for okay, maybe you don't have to watch it. I'll probably just link the document here as well that explains this, how they obtain the velocity mode. So this is a PID control, PID control for for the voltage, for the particular voltage, and so this is the, so yeah, I'll link that particular document, and you could sort of see how they come up with this particular equation here, this particular one, and it will make a lot of sense. How they come up with this equation. I'm not gonna go into that. And then after, so it essentially has some similarities with the position form PID control, but this is a velocity form, and it's more, it works much better for digital power supplies. All right, and then after that, after you compute that, so just look at that document, it will make a lot more sense. Um, yeah, but anyway, that's how you get the PID step out. And then after that, you have to sort of limit it, PID, the output limiting. So this particular PID routine is coded to have a maximum value of 1, because that's easier to work with than another sort of value. So 1. So if it's greater than 1, it will be limited to 1. If it's less than 0, limited to 0. And else, it will just do the normal what it calculated. And then afterwards it has to be scaled. Remember, the output of the PID routine for the voltage is going to be the set point, the current set point for the inductors. And so the variable used is our IRF total. So by IRF total, I mean the current flowing through here, flowing through that particular line there, wire, if you will, flowing in there, in that red part. So that's going to be the IRF total. So you have to sort of scale that max current multiplied by the PID control output. The max current you multiply it by the PID control output. And in this case, I made the max current, which is the IRF total. The max current is 18, so only a current greater than 18 can flow in here, which basically means max current flowing through each of these channels is going to be 9, 18 divided by 2. Anyway, so after the IRF total, now you can execute the current loop. Now we have the reference for the current loop, but the reference always has to be divided by 2 of the IRF total, right? So IRF1 is going to be IRF total divided by 2. IRF2 is going to be IRF total divided by 2. Okay, it's going to be divided by 2 basically of the total IRF. Whilst in the normal average current mode control, it's just IRF equals to IRF total directly, not divided by 2. Obviously, because it's one boost. Now there's two of them essentially in parallel in a weird kind of way, in parallel to one another. So you sort of have to share the current. The current gets shared between the two inductors, which is a big advantage of interleaved topologies. It's shared current through the inductors, so the amount of stress is shared between two inductors, two diodes, two MOSFETs, and the capacitor just gets everything in the end, your output. All right, so that's what that is, and obviously the same PID control routine is the same, just this time all the V's have been replaced with I's, and this time the output, when you're limiting the output, it's directly for the PWM, right? Instead of going into another loop, it's directly for the PWM. So control max is 0.8, right? 0.8. So the control max is 0.8 and the control min is 0.0. So control max means 0.8, that's 80% duty cycle, and the minimum obviously 0.0% duty cycle. So like I said, this particular routine is configured for maximum of 1. So whatever this puts out, it's if this puts out 1, that's 100% duty cycle. If it puts out 0.8, that's 80% duty cycle. So it's configured that way. And then at the end, it's scaled. So the max duty in this case is 159, so it's going to be multiplied by that to sort of get it to, because the 159 represents 100% duty cycle on this particular microcontroller, which is not a super PWM resolution, but it's good enough. It will do the trick. And the same for the second inductor. You have to do the control routine separately. You can't just do it once and then output the the how do you say, the PWM to both of them. Of course you could try that, but usually there are sort of, in especially in a hardware physical system, there will be slight differences between both inductors that you make. Um, I'm not saying you can't make both inductors perfectly to be like close to one another, but um, most of the time they'll be slightly different, and you sort of don't want to use the same duty cycle on both of them. So you wanna sense the current going through both of them separately to sort of account for it in control, right? So and then so that the controller knows the slight changes in the duty cycle to the slight changes to the duty cycle to give you the particular current that each of them needs, because they're not the same. They might be the same in a simulation, but in the real world, no, they're never gonna be the same. So, and not just that, the MOSFET and the diode, even even though they're from the same manufacturer, right? They're still gonna have slight differences. So you sort of have to do the PI control routine separately to account for that. And really, I keep saying PID control, but this is really a PI controller routine. Because if you look at the coefficients up here, there's nothing for the KD. 0 0.0, because I found that it makes very little difference when I change the KD. There is a benefit to adding a KD, but you sort of have to make sure you know exactly what kind of KD you want to use. Because for these particular coefficients, they kind of thumb sucked. Um, you know, not pulled out of thin air, but they sort of um how do I say, they sort of are holistically, I guess, are assumed. There's some assumed values there, and there's some trial and error going on. So you kind of don't want to add a derivative constant using trial and error is what I'm trying to say. You want to really calculate and make sure it's precise before you add KD value. All right, so for the particular coefficients, just go through this steps for the thumb sucked version. You should always start with this: KP equals to that, KI equals to that, and sort of work your way up. And always with double loop control, you always want to test the inner loop first. So to do that, you basically just do this here, like that. You uncomment, yes, you uncomment this particular line here. So what this does is it makes this loop void. It doesn't go into this loop because v loop count is 0, and it will never go into this particular loop because it will never get to 20 basically. And then in the main, you could sort of set up your iref, both of them, to whatever you want, and sort of check if your controller is able to get to those values. So let me just go back here and I sort of use this particular software cause remember it's microcontroller it's basically a microcontroller and a spice analysis together. And spice analysis are fairly I don't want to say super accurate, but they're a fair representation. And as for the microcontroller, it's very close. It's very close. When you simulate what a microcontroller is doing in simulation and in real world, they're very close. Because remember, we're dealing with ones and zeros here, as opposed to sort of an inductor, capacitor, diode, which are largely analog devices, and these sensors as well. But when we're talking about the microcontroller, it's digital. It's essentially the model of what's in the actual chip is the same as what's in here. It's the exact same model. Only the actual chip has some variations in terms of the VREF, obviously. So the VREF won't be 5.0 bang on. It'll probably be 4.95, 4.98, 97 thereabout. But in terms of the processes, the function of the microcontroller, it's very similar to when you simulate it. In terms of what it does with the coefficients, etc. So that's why you should use it. Usually more trust in the microcontroller simulations and control than with just the regular spice analysis. But it's a start. Obviously, the best is just to chug it in and try it out and see what you get in the real world. But you gotta start from somewhere. So I'm gonna simulate this now as so I'm just running that, and so the set point is 1.5. Or should I make it 2.5? I'm gonna make it about 2.2 each. You want to make them the same. Actually, now that I think about it, you could probably make them different and they will give different values, but it's better to have both inductors have the same level of load, not to overload one over the other, I guess. But you know, this is a simulation after all. So right, looks like that's gonna take a while. I'll just go back and explain some other parts. So essentially that's what you want to do, right? So you want to test the inner loop first, and once you see that it gets to the set point, the inductors get to the set point, obviously you design your system in such a way you can check the current flowing through the inductors, like independently, like a piece of wire or something, where you could like easily clip a current clamp around it and actually check what's going through the inductors. And you want to check the inner loop separately doing that, and you want to make sure the control coefficients are proper. Obviously you should always start with this coefficient, kp equals to, obviously it won't be fast, it'll be quite slow, but it gives you a start. And obviously there are different coefficients for both of them. You could obviously use the same, but just trying to be careful and conservative, etc. um this is a definition of the coefficients: kp, ki, kd. This is for the first inductor, this is the second inductor. So after you do that and you make sure that works, that it gets to the set point for the inner loop, then you're good to go. Then you can add the outer loop. And also when you add the outer loop, you want to add it with this. You want to go gradually. You don't want to make the inner loop unstable with the outer loop. And you don't want to go, also with regards to the speed of the outer loop, this value here, you could change that to 10, but do not go below 10 because it will make the inner loop stable. You basically not give it enough time to get to the set point, because it's too quick. It'll be too, it's better to have it above 10, essentially what I'm trying to say. And let's see here, yeah, so this is the kp and ki values. For the, obviously I've gotten creative with it and raised them quite high, but always start with this. It will be quite slow when you try it out, but at least you have a starting point. Okay, I can make it faster following these rules here, obviously. Making sure that ki is at least 3.5, making sure that kp is at least 3.5 times greater than Ki, and should be good. I think it's done. Then just say okay. And you see the readings. Go back. Um, go there. As you can see, okay, so I just realized that okay, looking at the waveform, it says 954. So I just realized that I didn't set the IRF total. So this should be 4.4, actually not. Because if I just set up IRF1 and IRF2 in the timer 1 routine over here, um, this is how it actually calculates. I actually have to set up IRF total for this to work out. Alright, so I can check now and run it again. So it's gonna take some time, I guess. But anyway, so you need to check that first and then add the outer loop afterwards with a conservative coefficient estimation KP and KI values, conservative values for those, and ramp it up slowly. So that's that. And yeah, I think that's about it actually. Well, just waiting for the simulation to complete. And well, you might want to consider using like I said before, DSPIC or STM32 or Texas Instrument or Renesas or any other microcontroller architecture that's optimized for this purpose, because microchip is more like a multi-purpose sort of thing, and it's more robust in that sense, whilst those other ones that I mentioned are much more focused on sort of um, digital power control. So they're optimized for that, for those reasons, for those things. Um, and it's important to note that you could also use a 2 poles 2-0 compensator, 3 pole 3-0 compensator for this, but I find that the PID has like a good balance between speed and ease of, coefficient of determining the coefficient, so it's more flexible to use, kind of easy to use, I guess, than a 3 pole 3-0 compensator, where you kind of have to be a lot more precise with your design. You actually have to calculate those values for 3 pole 3-0 compensator. Let me just check if it's done here. And right, so that's about well, the set point is 2.2, but it's not quite there. But yeah, as you can see, both are not gonna exactly look the same. I mean, look at that. I mean, it doesn't look the same on the simulation. You think it's gonna look the same in the real world? Absolutely not. So you sort of have to, that's why you have to control them differently. You need two different PID routines. Yes, routines for both of them individually. So that's why. So as you can see, yeah, I mean, obviously, if you look at that, it doesn't quite get there to 2.2, I guess, but well, it gets close. Look over there. But that's why you sort of want a controller with better PWM resolution, because then you can get closer to the value. So essentially, to get to the perfect set point that you want, if you're that kind of person where you set point of 2.2 and you want to get to 2.2, you need a combination of great ADC, high resolution ADC, and high resolution PWM. With the controllers, I find with the ADCs and microcontrollers, there are 12 bits in advanced ones. There are 12-bit ADC, but they're quite unstable. So if you want perfection, a perfectionist, you should get an ADC, an ADC chip, with a Sigma Delta ADC, a 16-bit ADC. So actually what this would do is it will sample the ADC for you and actually send the actual voltage to you with I squared C, high speed I squared C, obviously. So it will send that to you, and then you have the actual voltage. So I think you can get probably up to like 4 kilohertz of speed with this, which means you can get updates in 4 kilohertz, which is not super fast, but it's great for that accuracy. You can get that and pair it up with a high resolution PWM. That's you're gonna get to the voltage you want down to like 1 decimal place for sure, at least to 1 decimal place. So if you want 2.2, you get 2.2. If you want 2.25, I guess you're gonna have to go higher with the ADC resolution. Kind of going on and nothing there, but let me just get back to it. And so now that you've figured out that the inner loop is stable, now you can comment this line out, reloop count, and then run it again. And now you go back here. Now you can just take these out. Now you have to put this there, which is the output output voltage, which is what we want. And also keep in mind that your inductance for average current mode control, well, you have to operate in CCM. And what that means is the inductor size has to be relatively large. So now it's 600 microhenries, because remember you're trying to control the current through the inductor. Now you can if it's discontinuous. I guess you can, but it's much easier with CCM. If it's just continuous, right? So you want the size of the inductor to be high enough, such that it stays continuous at a particular switching frequency. And obviously, if you don't want this to be too high, then you're gonna have to increase the switching frequency. And on this particular microcontroller, that's pretty much quite difficult to do, because as you increase the switching frequency, then the resolution just dips, you know. So you want to do that on a much more advanced architecture, on a different microcontroller, not more advanced architecture, just a more specific for the application, tailored for that. IETI, STM, etc. So just keep that in mind. The inductor size should be large enough. You don't want it to be small, and obviously leakage is also a concern if you're trying to make it this big. So keep that in mind. Yeah. So now I'm just gonna run it again, and now the set point is 48.8. Alright, just run it. And also, for this particular inductor, this is unrelated to the code actually, just in terms of hardware. It's been used. I've seen it used before actually, where these two are coupled to sort of save hardware space. But with the coupled inductor, that also has a downside. Well, depending on how you construct it, if you use an E-core, then there's a risk of leakage inductance, sort of where at that point you kind of have to take care of the MOSFETs, design a snubber for them, because of the leakage coming out of the coupled inductor. But you think about it, having two inductors is a big space, but having like an extra, in case of an active snubber, for instance, having an extra MOSFET, having an extra MOSFET to having an extra inductor. I mean, most people would just choose an extra to having rather have an extra MOSFET or extra capacitor or tiny resistor. So it's a good trade-off in terms of space. This is just something interesting. All right, as you can see there, 48.8. I don't know why I chose 48.8. I guess to just sort of show that it can set point to a certain voltage. And of course, as you can see, I know it looks bad, but remember I've zoomed in, so it kind of fluctuates from 49.2 to 48 point, what's that, there, 48.3 and 49.2. Right, so like I don't know, I guess it looks kind of weird zooming in like this, so it looks like it's unstable, but it actually is stable. And also PWM resolution is a big issue this particular microcontroller, but it's good enough. Yeah, so that's about it. So that's basically average current mode control for an interleaved boost converter, which is a very interleaved topologies are really good in terms of sharing um, the current load. They have higher efficiency because you're essentially halving the amount of the parasitic resistance that the current has to go through. You're essentially sharing the current through two inductors, so essentially the resistance that has to go through is less, and in essence you have a higher efficiency. So interleaved topologies are really good. Great advancement in power electronics. Whoever came up with it, I actually don't know, but it's really good. And coding it. So this is just how you go about coding it. Um, on any microcontroller for that matter, the coding procedure does not change. As usual, the most important part is the hardware. If the hardware is crap, the code will make it worse. So ensuring that the hardware is proper, and of course, first off, the general topology of interleaved has to be proper. Power source, inductors in the proper position, MOSFETs in the proper position, diodes in the proper position, the right diodes, the right resistance. Obviously, not going too high on on this value here. Obviously, I went to 500 microfarads. It should actually be less than that. On 500 micro, you should probably go for something lower than that. Obviously, if you go lower with the capacitance lower than this, then you're gonna have to make your coefficients a bit larger because it will take more time to get to the set point, but it's much better to not have such a high capacitance in this kind of topologies. You see, when you calculate what you actually need, you actually don't need something this big. So that's something to keep in mind. And obviously, well, output, this is just a load. You might have any other type of load. And if your load is not switching, you essentially don't need a capacitance this high. If it's a switching load, you need something this high to kind of counteract that. Um, but in a continuous load, lower than that should be fine. And what else did I want to say about this? Yes, in terms of the importance of the hardware, so those things are important and connected properly. Everything, like I said, inductors, um, one can go coupled, and having to design a snubber for that to counteract that effect of the coupled inductor leakage, inductance, and all that. The hardware is super important. And secondly, the sensor placement. Okay, so the sensor placements are important. And in terms of what your goal is, are you trying to go for high efficiency? If you're going for high efficiency, then you have to use a Hall effect. current sensor. You have to use a Hall effect current sensor for this. Um, yeah, you have to use a Hall effect current sensor. But if efficiency is not such a big concern, like let's say you're okay with shading, I don't know, 0.05% of that efficiency, or in some cases 0.5% shading that off, then you should use how do you say, um, a shunt current resistor. Well, the advantage of the shunt is that the readings are much more stable than Hall effect, and yeah, Hall effect sensors are great, but sometimes they sort of struggle in these kind of situations. And obviously, you could go with more high-end stuff, high-end current sensors. You know, they're also Hall effect, but they're more stable. You could use them, but they're more expensive. Um, I knew of one, but I kind of forgot the name of it. But they are sort of high-end ones. It's kind of expensive. Um, Usually, personally, I like to. I don't get too obsessed about how high the efficiency is, so I sort of like to use shunts here so that I can control the current going through here better. But you know, it's a choice. If efficiency is a huge concern, then you probably should just go with the Hall effect here and sort of deal with the inaccuracies in the. Well, the thing is, they're inaccuracies, but well, not inaccurate, but not super precise, right? So they fluctuate quite a bit, but you can sort of the controllers, the PI controller is sort of deals with that in the long run, and sort of deals with that, so it doesn't cause too much of a problem control wise. It's just not very precise. That's just the thing. It fluctuates quite a bit, and that's it. And also for this part here, for the voltage sensor, this is also important. And in the real world, you'd actually add capacitor in parallel to that. Um, you have to add the capacitor in parallel to that, sort of 10 nanofarads, well, depending on what this resistance is. Sort of is like how do you say, it's a low pass filter. Yeah, it's a low pass filter of sorts. So you add a capacity here, because resistors are not so perfect in the real world. So and noise is a thing as well, so you're gonna have to deal with that. So the sensors are very important. You might want to add a, how do you call it, a voltage follower with an op amp to it to sort of protect your microcontroller. But sometimes in the high speed applications, you sort of want to let go of that op amp and not use it, but and just go like this with a capacitor in parallel. But you know, your choice. But the most important thing is that your sensors are placed properly, and so that you can get readings into the microcontroller, because the code literally means nothing if the hardware is not giving it proper readings. So you know, sensor placement is really important. And in the microcontroller ADC, ensuring the ADC, if your ADC is not working in the whatever microcontroller you use, there's no need to go ahead, because you will get absolutely nothing. Obviously, ADC is very important in functioning of control. And that's about it with average current mode control. Um, it takes a bit more care than just regular control, like just voltage mode or current mode control. You have to take more care with it, but you know, but it's rewarding. I mean, look at this. I know this is not perfect, but if you look at compare this to like a voltage mode control, it's sort of, and you take a look at the current going through the inductor, it's just ridiculously, it's ridiculous. And you sort of have because the current going through the inductor is what's also going through your MOSFET, so you have your converter is probably not going to last that long with just straight up voltage mode or just straight up current mode control. I'm talking about the output here. If you're just controlling only the voltage here, directly, and you're not controlling the current, you're just controlling the voltage only. I'm talking about that. Then the current going through your inductor is going to be kind of crazy, okay, because you're not taking it into account and controlling sort of. It's going to affect your MOSFETs in the long run, and that's the issue. Um, all right, I think I've spoken long enough. Um, and that's about it. I just hope I haven't forgotten anything. Well, if you've got any questions, and you just ask. Um, but this is pretty much it. This is pretty much how the procedure goes, and yeah. So that's it. So all the best in your various applications. Cheers. Bye.